Welcome to my talk on antenna array simulation and design automation. So we've seen a lot of antennas, range of different antennas. Now I'd like to focus a bit more on the arrays, arrayed antennas, so to speak. So just as sort of an overview of what I would like to touch on, there's really plenty of things to touch on today, and I'll scratch the surface on many. Hopefully, it will encourage you to go and look at our knowledge base where we have application notes, QAs on these. But I would like to give a quick introduction to the array task and briefly touch on infinite arrays and then move on to array synthesis in Antenna Magus, talk about finite arrays and the modeling and simulation thereof, and then really get into the depths of the solver technologies that we do have available for different types of finite arrays. And finally, I would like to end off with just a quick look at the Subarray workflow that we recently introduced. But I would like to start by showing just a quick demo of the array task, and I will do so by using a multi-band shared aperture MIMO array, and just to show you how quick and easy it is to set this up. So in the schematic environment, I have 3 different blocks, 2 different radiators, and 1 radome. I just loaded the array layout, and now I'm just going to specify which of these elements would be using which model. So there's a high band and a low and a mid band element for a typical base station application. I specify then also using a specific platform, or in this case a radome with a backplate. And so once I've done that, I need to go on and specify actually what the excitation should look like, and I select multiple excitation lists because I have predefined lists that I want to use in post-processing. Next, I go to the element excitation settings and I go and specify firstly, which element should be driven. So I'm selecting the high band, and I'm saying that they should be driven individually because it's a dual linear polarized antenna. So the 2 ports need to be individually driven. I create the simulation project. In this case, I select the frequency domain solver, just the reference frequency, and I select sequential excitation, where all the ports will be excited, and in post-processing, combined results will be done. So here you can see the model then that's quickly assembled, all these different elements. And you can also see the decomposition of the computation domain. And we do a quick find all so that it's able to find and group elements or domains of the same geometry together to exploit that in the decomposition calculation or in the domain calculations. And basically you can see then once the results are finished, I have all the ports excited. So you see the embedded element patterns, and then you get the combined results as well, which is then a post-processing step. I can sweep through the excite list parameter, for example, update the combined results, and basically it loads one of the excitation lists that I predefined. You can also see then the cross-pol and the co-pol there, because as I said, there's 2, it's a dual linear array. And you can see then I can even apply scanning on top of this. So basically I update it, and you can see the tilt that was specified, and so the phase calculation is automatically done in the background and adopted by this array simulation. And even in this case, it might get confusing because you have so many excitations and you're sweeping between lists and going between scan angles. You can go back to the array task, select the simulation project, and you get this excitation viewer that you see here. So you can see the progressive phase shift, for example, in this case that was specified. So with that, then the array task is really a task that helps you to automate modeling, helps you to automate the simulation setup. So we already briefly looked at some of it, but let me just get into more detail. So when you create an array task, there's different 2D shapes with varying lattices that you can select of. So really standard periodic structures that one can specify. You can also set which elements are active, which should be passive, so just terminated with its characteristic impedance, which are set to be empty. Or as I just showed in, okay, so before I get to that, then there's also, of course, the typical magnitude tapers that can be selected. Quantization errors can be introduced both in phase and amplitude. So there's really a range of things that can be quickly set up for the excitations. And then, as I showed in my demo, one can also load, an existing file, a TSV file, where you have tab separated the positions, excitations, and even rotations, because we also support conformal arrays. So with such a project, however you've defined it, when it's periodic, you can go and define a unit cell simulation project, which is basically the infinite array, where the active element pattern and impedance, port isolation, things like those are quickly calculated. And then also one can create a full array simulation project where you can do beam steering, and of course the finite edge diffraction is taken into account. For more information, you can always refer to this QA that's in the knowledge base reference at the bottom. So let's quickly talk about the infinite array. In this case, we are making use of Floquet modes, and I think for those of you with a background in arrays would be well familiar with the subject. So the point is that the array task sets everything up for you. It's completely parameterized, sweeping these, over the scan directions of the fundamental modes and getting the right phasing. All of this is automatically done. And here you can see, for example, when it's scanned towards zenith, you can see the wavefront. If I move to a theta 30-degree angle, you can see the wavefront again there, and basically the energy exiting the right-hand side is just entering on the left-hand side, and that's how you sort of emulate also this coupled environment. And for example, in this case, you are actually exciting a surface wave or sort of a evanescent mode. And you can see how the wave propagates along the surface. And so in the end, all of this quickly calculates for you the active element impedance or reflection coefficient on the left-hand side, where you have on the y-axis the scan phi and on the x-axis the theta scan angles. And you can observe there the scan blindness as well, where there's total reflection. As we just saw in the one animation. And then also on the right-hand side, you have the active element pattern, so basically the embedded pattern in an infinite array environment. And again, you can observe the blind spots there. So this is good to run these before you move on to the finite array, just to really make sure that your radiator design is foolproof for the periodic environment that it will be placed in. Now, before I get to the finite arrays, let's quickly just talk about array synthesis, because I think many people are aware of Antenna Magus, but they're not maybe familiar with the synthesis tool that it has for arrays. So basically, there's all the regular sort of layouts, linear, rectangular, circular layouts, concentric circles, circular rings, so a bunch of things that you can specify, the beam, the side lobe levels, the scan direction, even getting nulls and things like those, even triangular lattice, cylindrical, and then also recently introduced a class of spiral arrays. And basically, once you have synthesized your array factor, you get this distribution matrix, which you export and import in this TSV format, which can be consumed quickly by the array task. Now, there's other operators as well. You can use you can work with these layouts and translate them. You can conform them onto certain shapes when it's conformal arrays or these segmented arrays. And then, of course, as we have in the array task, also the discretization of magnitude or phase distributions. Now, one interesting point here is maybe the spiral arrays, where we've recently introduced these, and essentially using a Fermat spiral and making use of a golden angle for the spiral. This leads to really a non-periodic layout that has a sunflower pattern. So if you look there on the right hand side in the middle, the sunflower one, you can see the layout, how that looks like. And then there's more that one can do with this, because let me maybe just give some background for the benefits of such a non-periodic layout. Essentially, the aperiodicity, of course, then suppresses the grating lobes. So you don't have the constructive interference that would cause a grating when you have sparsely placed elements. And you can see that then on the curves below. And for the rectangular case, you can see the big grating that's popping up there. But another nice thing is that you can also do a spatial Taylor distribution, of course, and suppress the side lobe levels without doing amplitude taper. So that's to the right-hand side bottom, you can see such a spatial Taylor distribution layout. So they get very big. But again, the nice thing is, even though you're talking about more than half a wave, more than one wavelength spacing, the point is that when you're working at millimeter wave, things get very small, and it gets increasingly tough to integrate feed networks or manage the thermal properties, between the front-end electronics, and that's also where these layouts gets very interesting and useful. Okay, let's move to the finite arrays, then coming back to the array task and what is offered there once you have decided on your layout. There's different ways basically to simulate these full arrays. There's first case, we're talking about simultaneous excitation, so having all the elements excited with complex weights together, or there's a sequential excitation where you're combining everything in post-processing, and there's even a group sequential excitation, which I will get to in a minute. So let's maybe just quickly run through these so you can also see how the UI looks. So we start with a simultaneous case. This is basically where you have just the excitation list that's completely parameterized by the array task, controlled by the array task with the excitation management. So when you specify phi theta scan angles, those are then calculating the phase shifts automatically, and this is done for you. But as I showed, you can also load multiple excitation lists beforehand, and they are just populated then in the solver excitation list, and you're able to control the sweep through the indexes. In this case, you can see there we have 4 lists, but there's 2 ports per element. So basically, it's a dual linear polarized array, which means you end up with 8 excitation lists. One nice feature that we also added was for the time domain solver in 2024, you're able to now also support these, so you don't need to do a parameter sweep through the lists. They are already available for you, and sequentially these are executed. Then we get to the case where you are exciting all ports, so a classical sequential excitation. This is where all the active ports are calculated, so you see all the embedded element patterns there, and they are just combined in post-processing using then the weights coming from the array task. And then there's the other case, which is simulation zones. So let's say you have a really large array, and essentially parts of the array or some elements really have the same. There's a lot of these elements have the same environments, essentially coupling environments. So basically what you do is you group these elements together. So you can see the different colors here. You can see, for example, on the edge there, I mean, firstly, I do have also a sort of zero padding on the edges. So I just have one group, which is shown in yellow here for the edges, and you see the reference element there. So basically that reference element is calculated and it's reused for all these yellow elements. Same we do for the center elements. And so this is a good approximation then. And one can even introduce or exploit element symmetry as well, if that's possible, and then have even less grouping or less elements to calculate. So in this case, there was only 9 element patterns calculated, and you can quickly reconstruct the full array pattern with the complex weights in post-processing. So all of this is automated basically for you. Okay, sorry, I'm going a bit fast, but I realize there's so much to get through and we are sort of running behind time a bit. So this brings me then to the solver technology, because it's one thing to automate the setup, modeling, everything. It's another thing to actually solve these really large problems. And as you know, CST Studio Suite has many different high-frequency solvers, time domain, frequency domain, and integral equation. When it comes to time domain solver, it has 2 different methods. One is the finite integration technique, or FIT, which is really our flagship solver, and it's very robust with a PBA technique that it uses. So not having any staircasing or anything like that, being able to work with thin sheets, crossing hexahedral meshes, and it really outperforms the classical FTTD methods. Then there's the second method, which is the transmission line method, or TLM, which actually uses lumping for the hex meshing, so similar to an octree style, where basically this is very attractive when when it gets very detailed for a really large model, because of course the smallest element that you have dictates basically the timestamp, the time step, because you have to push time signals through the system, right? So it can take a lot of time, and this is where TLM can really shine. Now, both are ideal, of course, for broadband results. Both support GPU acceleration. And then there's the frequency domain solver, which we've been using for infinite arrays for a long time with Floquet modal analysis. But we've also recently introduced domain decomposition method, which is well suited for the large array models with complex details, where we're able to then exploit repeatability within an array geometry to really speed things up. And might I also say, I mean, just coming to the finite element method in itself without DDM, with a direct solver, it scales very well with many excitations. Although we would recommend just DDM in such a case. Then there's also integral equation solver, of course, for large structures would be using MLFMM. It discretizes basically only the surface, so of course avoiding just sort of a lot of elements in the volume or in the background, and it works well for structures that are of course predominantly metals, although of course it supports dielectrics as well, and also for acceleration GPU can be used. Okay, let's get to one benchmark just on the time domain methods, because I think this is always useful when we're talking about these very nice solvers, just to get some real numbers out. In this case, we have a Vivaldi antenna array with dual polarization, and it's an ultra wideband model with 256 elements, and it's executed on 2 P100 cards. And so, yeah, let's just look at how they stack up. For the FIT, the finite integration technique, you can see 97 million hex mesh cells, and this is executed, so a single excitation basically, or basically everything simultaneously excited. You're looking at about 34 minutes on these 2 GPU cards, so really very quick, and then with a total of 60 gig memory usage for these cards. These benchmarks were actually done in version 2020, so quite a bit older. Sorry that I couldn't give you more up-to-date results for this, but nevertheless, you can see how this then compares with TLM, where, of course, there we are doing lumping, which I already mentioned. So you can see the mesh cells are a lot less. You're talking about 6 million mesh cells, and the memory requirement is only like 4 gigabytes. This Does, however, take a bit longer, 46 minutes, but still you get the results and they look very good. You can see when you compare just one cut here, side lobe levels, everything are fairly spot on. Talking about solvers and how they compare in terms of fidelity, because I think for those of us also used to measuring, it's you know that sometimes it's good to go and measure as well. I can tell you we have many methods, and the point is you can actually get these stacked up against each other and really with surety show that results are converged before you prototype anything. So in this case, we have some results from just a benchmark we did for a customer, so confidential model with a lot of detail in it. I can tell you. You can see we used the domain decomposition, DDM, FIT, and TLM, and you can see the return loss, how this is compared over frequency. You can see on the right-hand side also the far-field efficiencies. So everything really spot on. And then when you go to the far-field cuts, also spot on for this elements and the cross-polar ratio on the right-hand side corner. So yeah, this is very useful just to give a bit of confidence also in these methods. Now, of course, you have to select the right solver for the right problem. So in this case, we have the shared aperture array where it's MIMO array, which means you want to excite all the ports individually. In this case, we talk about 68 ports actually for the high band elements. So as I said, it's a shared aperture. We're looking just at the high band elements, and we're looking at about 9.9 million TET mesh cells. So for a direct solver, this is out. It's not going to be possible, but we make use of domain decomposition, and we run this on a single machine. So a single machine with 48 cores. Of course, it's a good processor, but the point is this is a really large model. So I want to show you how this have also improved to version 2024, because we just a few years ago introduced this solver. So we're every year really with the major releases bringing a lot of improvements, and you can see this by looking at the numbers. We have the peak memory that is definitely reduced, going from 2023 Service Pack 5 to 2024. You can see also the time per frequency sample and the overall runtime, how much that improves. So within less than 5 hours, you can get 68 ports calculated for a model that is 1.2 meters in length, which is about 15 wavelengths in this case. So really good results that we see there. So this brings me then to just briefly the last topic, which is the topic of subarrays. We recently introduced this functionality in the array task that you can configure it with subarray elements. So each of these elements actually represent a subarray, and you can see then the same way you can select shapes and things to specify for the subarray as well as the element model being used. And in this case particularly, we have implemented the workflow for circular polarized phase arrays, because they typically use this configuration where you have 2x2 elements and they are fed in quadrature. So used a lot for SATCOM applications, and you can specify then whether it's right-handed or left-handed. You can switch between these as well, and whether it's counterclockwise or clockwise, the rotation of these elements. So without getting into too much details, I think the proof is also in the pudding here. If you do look at the results of a finite array, and this one is actually scanned in the diagonal plane, you can see no gratings popping up or cross-polar levels really being well under control, because we do this quadrature phasing. And you can see then basically, in the UV plots, right-hand circular polarization, and then at the bottom the cross-pol, which is about what is that, about 20 dBs down on this particular in this particular case. And then a nice thing is that we have not only automated building and setting up the finite array, but you can also use you can also do a unit cell simulation, so infinite array of the sub array, so the 2x2 elements. And you can see there the active element pattern towards on the left-hand side with the radome taken into account. And then the nice thing is when you start comparing these values, you see it's actually very, very close. They correspond very well, where on the right-hand side for the full array, you have edge diffraction as well, right? So you can see here the total radiation efficiency fairly similar at about minus 0.55 dB or something around there. And then also the actual ratio being at 2.3 dB. And then as you're scanning down, so in this case, we're scanning to theta 30 degrees in the diagonal plane, you can also see the scan loss. So basically the loss from zenith to this scanning point. So the aperture reduction sort of, you can see it's around 0.7 dB in both cases, taking losses into account as well from the material losses. Yes, so this brings me then to the conclusion. Hopefully it was not too fast and you could at least catch a few points there. The array task provides automation in both modeling and simulation setup, and it enables the engineer to really do initial design explorations or even to optimize for performance at different stages. So we've been talking about unit cells, but also the finite arrays, or just approximating finite arrays by using simulation zones. And then there's a range of solvers. So for all the different applications, there's specific solvers to choose from, and even verify results by doing single port calculations with one or the other. And yeah, as I mentioned, having the option of three fundamentally different solvers or methods, it really provides then the confidence needed for high fidelity results. So that is my talk. Thank you for listening.